What we're going to talk about today is Bushong Chapter 1. First, I'm going to run through the course outline for this semester, this being the first section of this semester and the first chapter of the book. So this is coming out of Bushong's 12th edition, and this recording is going to come with a couple of apologies. One is that I have never taught out of Bushong off of PowerPoint, and number two, I don't think I've done a whole lot of teaching out of Bushong without an audience in front of me. So this is going to be a little bit awkward, but also I want to apologize for my voice. Obviously, I'm still trying to get over this stuff. I don't know how long this is going to take, but until I'm fully healed, then this is kind of what you're going to have to deal with. All right, so what we're going to do this semester, this week one, and Amy took my class on Monday, so I could have a little bit more time to prepare for today. And I'm going to link the video below for the physics overview. But this is the first portion of this text in this chapter that will be testable. So what we're going to talk about today is we're going to talk about essential concepts of radiologic science, nature, surroundings, matter, and energy. And then next week we'll talk about ionizing radiation, discovery of X-rays, and we'll walk through the rest of chapter 1. We'll have a test somewhere around week 3, and I'm going to talk about that a little bit more. And then we're going to start on chapter 2, which is basic physics. So we're going to talk about how things interact and how physics work. Then week 4, we're going to finish that up, and we'll start with chapter 3. This is the structure of matter. We're going to talk about the different types of atomic structures and the different theories behind atomic structures and the development of the current atomic structure that we use now. So we'll talk about that for a couple of weeks, and we'll have a test on that. And then we'll start with chapter 4, which is electromagnetic energy. So this is where it really kind of gets a little bit dicey. Students have some of the students will struggle with chapter 3, but chapter 4 is where it starts to get a little bit more complicated. So we'll walk through chapter 4, then we'll get into electricity, electrostatics, electrodynamics. Electrodynamics will finish up on chapter 8. We'll have a test over chapter 4. We'll start with electricity, magnetism, and electromagnetism after that test. We'll go through week 9 talking about that. And then we'll have a test on somewhere around week 10. Again, we'll talk about that again a little bit more in depth here in a minute. So then we'll start with chapter 6. That's finally we're getting into the X-ray imaging system and different components of the X-ray imaging system. And then around week 12, we'll have a test over that. Then we're going to break apart the imaging system. We're going to talk about, especially the X-ray tube. And we're going to talk about external components versus internal components. That's chapter 6. That says chapter 7. I apologize. It should be chapter 6. Internal components of the X-ray tube. And then we'll finally get to chapter 7, and that's X-ray production, interactions in the target, emission from the X-ray tube, and how our exposure factors can be adjusted to affect a change on the image receptor. And we'll finish up the semester with chapter 8. Chances are we're not going to get to a test over chapter 8, and I can't remember the last time I actually had a test over chapter 8. And then we'll have a final exam on week 15. So I'll come back out of that. No, I did not really want to do that. Just to pick up with the very first part of the chapter. So let me go back to the testing. So the testing schedule for this semester is really pretty loose. I have to put tests into specific weeks, especially for the online syllabus. And we're going to try to stick as close as possible to the testing schedule, but if we have to make a little bit of an adjustment because we need to spend a little bit more time on some concepts that we're having a hard time getting through, then we'll certainly do that. So even though our test here says test is going to be on week 3, if we finish up on Wednesday of next week, we very well may have a test on Friday of the week before and go ahead and start with the next chapter. So the test, 2 things about the test schedule. One is that we'll expand it or contract it as we need, not by much, but also what I'll try to do is not have tests on the same day that Amy has, so that it'll free up a testing schedule just a little bit and make it a little bit easier. Can't do anything about the lab. Whether or not it falls on a lab test day is, I can't do anything about that, but I'll try to keep them off of Amy's test days. So nature of surrounding, this just comes straight out of the Bushong book, and we'll follow it pretty closely, but my job is to kind of dial things in a little bit tighter for you. So everything is either matter or energy. So matter is anything that occupies space and has mass. It's made of atoms, and even some of the things that you see, well, all the things that you see are matter. But some things that you don't see are matter as well, because they're made of atoms. So oxygen, air, surface air, which contains oxygen, are also mass. We have a tendency to not think of them as mass because 1, we can't see them, and 2, they just don't affect us very well. But you wouldn't feel the wind if it didn't carry any kind of mass with it. So it has atoms, and therefore it is mass, and that it has mass, and therefore it is matter. So what we have a tendency to do is kind of conflate mass and weight, or matter and weight, and it's not really the same thing. The online videos that I'll also post to this, I'll walk through a experience I had with my son going to space camp in Huntsville, Alabama, and that would have been a very long time ago. He was probably 6 and he's 32 now, so you do the math. It's been a while. So what we got to do there is to play on some of the simulators. And one of the simulators was what they refer to as the 1/6 chair. It's what they train astronauts to walk on the moon. And if you see astronauts walking on the moon, they don't really walk, they hop. And that's because they can't get traction because there's not enough weight pulling them down. They don't have enough weight on the moon to walk well. So they do this hopping motion. So if their mass is the same on the moon as what it is here on Earth, and their weight is different, that means weight and mass are not necessarily the same thing. Even though we tend to make an equivalent, like if you happen to be somebody who goes to the gym, you'll see those big iron plates that say, I think it's 22 kilograms or whatever. We have a tendency to make a mental comparison between mass and weight, but they're not really the same thing. Weight is the effect of a mass or gravitational pull on a mass. And in that, different planets have different gravitational pulls. So if you were to take that same mass, let's say you weigh maybe 200 pounds, let's say, and you were to go to the moon, then you would weigh 1/6 of what you would weigh here on Earth. If you were to go to Jupiter, you would weigh, I think it's 2.5 times more. So again, your body doesn't change significantly anyway between here and the travel that you would take to the moon or to Jupiter, but the difference would be the gravitational pull on your body. So weight is just the effects of gravity on mass. So how we measure mass is really with kilograms. Weight we measure in a lot of different ways, like pounds. We can use pounds for weight or stone or something like that. So we've got a couple of different analogies that we can look at as far as our weight versus our mass. All right, so we already used one, and that was the moon versus the Earth or any other planet. But water is a fascinating substance. It can be one of three states. It could be liquid. It could be gaseous, in let's say clouds or vapor, or it could be frozen, solid. All right, so you've got three different states there. But if you think about the way water behaves in each one of those states, then you can again see the difference between mass and weight. So if you were to take ice, a quantity of ice, and drop it in the water, and it had the same weight, then it would not float at the top of the water. It would probably find some specific density, like somewhere in the middle of the body of water. But it doesn't. It floats at the top because ice is lighter than water. So the liquid version is heavier than the frozen version. The odd thing is, though, also, is if you heat it up enough that it evaporates and it goes up into the air, it's also lighter. It expands, it gets bigger, and it's also lighter. So back to the ice analogy, if you freeze ice, it also tends to get larger. And you can see that if you were to put, a soft drink in the refrigerator, or not in the refrigerator, but the freezer. You put it in the freezer, and in a lot of cases, what you'll get is a distortion of the can because it's going to swell. So again, water can be in one of three states, and it's going to have different weight. But if you were to gather all those water molecules back together and eventually weigh those, then they would have the same weight. Also, think about different substances that weigh something different. You can have two different sizes of one size of two different materials. So if you had a piece of lead that was about the size of your laptop, let's say, then it would be quite heavy. I don't know exactly how many pounds it would be, but it would be heavier than if you had a piece of aluminum exactly the same size. So the weight would be exactly the same, but the size would be exactly the same. So the mass would be exactly the same, but the gravitational pull on those things would be totally different. The lead would be heavier than what the aluminum is. So in addition to mass and matter, the other nature of our surrounding is we have energy. So energy is what powers things, right? So we get energy from the sun, and matter and energy are interchangeable. And that being said, you have to have specific things in order to make them interchangeable. What I mean by that is that we get energy from the sun, and it allows things to grow. If you were to put, let's say, a bucket on your grass and not move the bucket, the grass is going to die, right? Because it doesn't get any sun. So the sun interacts inside of the plants and causes them to grow and helps them to grow. So it's conversion of energy to matter, the sunshine being pure energy. So there is a energy mass equivalent. And that doesn't really describe it all that well, but let's say you've got a tree. You've got a tree down and you burn the tree. What do you get out of that interaction? What do you get out of the burning of the tree? You're going to get light, which is energy. You're going to get heat, which is energy. You're going to have some matter left in the ashes, but for the most part, you're going to get a lot of energy out of it. So how do you create energy, how do you create matter with energy? Again, the sunlight, but also the nutrients in the soil. If you plant an acorn, then the acorn splits open, the tree starts to grow, the sun hits it, helps it to grow. So you've got the chemical interactions, and we're going to talk about chemical energy here in a minute, but the chemical interactions in the tree absorbing those nutrients along with the sun creating the photosynthesis allows the trees to grow. Energy creating matter. Cut the tree down when it gets big enough to make firewood out of it, and you can have matter creating energy. So energy, just the definition of energy is just the ability to do work. And then we've got a lot of different types of energy. So we're going to walk through, and this picks up on page 4 of Bushong. So we have a lot of different types of energy, and we're going to walk through how we use each one of these things. So potential energy is just that. It's unrealized energy. It's an energy that we can use if certain circumstances exist or certain things happen, right? So it's an energy of position. So think about your cartoons. You may have to go back to some old school cartoons and look at things like the Roadrunner and the Coyote. But let's say you've got a rock on the edge of the cliff. Is the rock doing anything? And the answer is no. But if you push the rock off the cliff, does it? And the answer is yes. So you've got matter in motion creating energy there. So potential energy is just energy of position. It's unrealized energy. It can happen if, we can get energy out of it if certain things happen. So it's potential to do work by its position. It's stored energy, essentially, is what it is. All the different types of energy, and we're going to talk about each one. Kinetic energy is that realized potential. So you push the rock off the cliff, and you've got energy of motion, and that is kinetic energy. Chemical energy is energy inside of a chemical reaction. So Bushong uses the example of dynamite, which really with dynamite, you've got to have some sort of instigating event to make dynamite explode, so you have to add in thermal energy. But chemical energy, a good example of chemical energy is your digestive system. You put food into your system, and what you get is energy, essentially, right? So you create calories to make available in your bloodstream for your muscles, for your brain, so that you can go do stuff. So that's chemical energy. But also, you see chemical energy in batteries as well. Certainly, we have chemical energy whenever we mix acids and bases. We can get explosions there as well. So a lot of different ways that we can get to chemical energy. Electrical energy is movement of electrons or movement of electric charges. And really it is electrons. We don't move protons through electrical systems. We use electrons. They're easy to move. Protons are not easy to move. So we move electrons. So they're all negative charges, but it's movement of electrical charges. Also with electrical energy, we have to have something that causes that electrical energy. And that could be mechanical energy in the form of of generators creating that. It could be nuclear energy driving those generators. So we have to have something to make electrical energy. In most cases, we can't have static electrical energy. And we'll talk a little bit more about that later on. Thermal energy is kinetic energy at the molecular level. So you're going to hear this. You rub your hands together, and what you get is warmer hands because you've rubbed your hands together. All the molecules in your hands are rubbing against each other, and what you get is heat off of that. So thermal energy is really heat. We'll measure it in Fahrenheit or Celsius. What you're going to learn is that what we use here in the United States is not the normal scientific measurement. So Celsius is more widely accepted. So it's measured as heat. The more motion you have, the more heat that you're going to create. Sometimes you're going to have overlap between energy types, like electrical energy. Whenever we have truly movement of electrons through a circuit, then you're going to create thermal energy. And more on that here in just a moment. Nuclear energy is the energy that's contained within the nucleus of the atom. And whenever that energy is released, we can get a lot of electric energy. We can get nuclear explosions, which are obviously devastating. But it's the energy that's contained within the nucleus of the atom. And then we have electromagnetic energy. And that's any kind of energy that demonstrates both an electric and a magnetic property. So, those would include radio waves, microwaves, visible light. So electromagnetic energy, visible light is electromagnetic energy, infrared radiation, X-rays, and gamma rays. So all of those are different types of electromagnetic radiation. The difference between those levels of electromagnetic radiation are their energy levels. And we're going to talk about those energy levels whenever we get into the chapter on electromagnetic radiation. So again, energy and matter are interchangeable. Matter can use energy. Matter can create energy. Energy and matter can be transformed from one type to another. And energy can create matter as well. So why is all this important? Well, because we use every one of those. So let's back up a little bit. What you're going to find, what you're going to find whenever we get into later in the semester is we're going to use the word electric potential or potential energy to describe one of the technical factors that we use to control the X-ray beam. We have two. We have kVp and we have mass. Mass is really a product of two different things, and that is milliamps and seconds. So we're just going to call it mass at this point and assume it's one thing. But kVp is a totally different thing. So kVp controls the energy level of the X-ray system. And when we create X-rays, what we're going to be doing is we're going to accelerate electrons from a filament to a target. And the interaction is going to be very violent as those electrons smack into that target. Then they're going to create a lot of different things, or a number of different things. They're either going to complete the circuit and with the movement of the electrons create more heat, or potentially they're going to create X-rays. So the higher the kVp, the faster the electrons travel from the filament, which we're going to call a cathode, to the target, which we're going to call an anode. So it's the X-ray tube itself is what we refer to as a diode. It's a vacuum tube diode. And we're going to send those electrons across the tube really, really fast. And the higher the kVp we use, the higher the speed that we use to send those electrons across the tube. So if we use 100 kVp, then they're going to travel across the tube much faster than if they travel across the tube at 50 kVp. So it controls The kinetic energy, the speed with which the electrons travel, because it controls the potential difference, the relative positive and negative charges between the cathode and the anode end of the X-ray tube. So the higher the kVp, the higher the potential difference. We'll refer to kVp as potential or electric potential. So kinetic energy is once we apply the kVp, you push the exposure button. If you've been in clinicals and you've paid any attention, you'll notice that to make an X-ray exposure, you've got two different buttons, or you've got one two-position button. That is one two-position button. All right, so with the two buttons, what you've got is a prep button. When you depress that prep button, then what you do is you collect the electrons on the filament. The electrons are not traveling across the X-ray tube yet, so you have potential energy. Once you push the exposure button, you apply the kVp, and the electrons travel across the tube really, really fast, maybe a third of the speed of light. They're going really, really fast. So that is your kinetic energy. Once you depress the exposure button, you send the electrons across the tube. We're going to skip over chemical energy, and we're going to talk about electric energy. We'll get back to chemical energy in just a minute. So the electrical energy is what we're sending across the tube. We're sending electrons. We collected the electrons on the filament, and then we sent them across the X-ray tube basically in a miniature lightning bolt. So that's electric movement of electric charges. That is electrical energy. So anytime we take electrons and we move them through a circuit and we congest them, then what we're going to do is we're going to create heat. That's how the heater in your house or your car works, essentially, is that you're going to send electrons, well, not in your car, but in your house. A car is a discussion for a different day. But what we're going to have is a collection of electrons, or better than the house, let's say your oven, because you can see that, or your toaster. If you push the plunger down on, on the toaster, then what you can see is that the coils inside there get hot. The reason they get hot is because you've congested electrons. So movement of electrons create thermal energy. All right, so we can get that electric energy from a nuclear power plant or something like that. So any kind of power plant, really, but nuclear power plant works as well. And what we're hoping to do is once those electrons slam into that target is create electromagnetic energy. The dirty secret about X-ray creation is that only about 1% of the electrons we send across the X-ray tube become X-rays. The rest of them just become heat. So the main thing that we create in the X-ray tube is heat. Oddly enough, the worst thing that we can create in the X-ray tube is heat. So we have to deal with the heat, and we'll talk about that later in the semester. So let's go back to chemical energy and talk about that again. So chemical energy is one of the examples was batteries. So our X-ray machines, we prefer to bring the patient to the X-ray department to take an X-ray. But sometimes the patient's too sick to make the trip to the X-ray department. So we can take an X-ray machine to the patient's room. That X-ray machine is going to work off of batteries. So back to the top of this, how are we using all those? Well, the potential energy is controlled by the kVp that we use, which in turn controls kinetic energy. Once we release that potential, we can get that, that energy from batteries, but it's electrical energy that we're going to convert we're going to convert electrical energy into thermal energy, that thermal energy into electromagnetic energy, and maybe, we get some of our energy from nuclear energy. So a lot of different energy types, and the reason you need to know each one of those is because each one plays a part in the operation of the diagnostic machine. So radiation kind of gets a bad rap. Radiation just means movement of energy through space. So not all radiation is necessarily harmful. It can be. Heat can be harmful if you get too close to it. It can burn you. Sound can be harmful if you get too close to it. It can damage your ears. So it's not necessarily harmful, but it can be harmful. It's just movement of energy through space. So some energy types require a medium, like sound. There is no sound in space. So what sound needs is vibration of molecules. And the reason we can talk to astronauts while they're in space is because inside the capsule or space shuttle that they're riding in, there's oxygen that's been pumped in there. It creates an atmosphere. So they can talk, and because they've got an atmosphere with oxygen and molecules that move, then they can speak. And then a radio transmitter picks it up. And the radio transmitter does not need any kind of medium. That's electromagnetic energy that is going to send the signal to the Earth. So electromagnetic radiation, though, is a specific type of radiation. And it is anything that behaves, and I say mostly like light. X-rays behave like light in certain ways they do. Okay, so it travels in waves, travels at the same speed, and that speed for this particular lecture just needs to be the speed of light, right? That's why we call it speed of light. It's because it travels at the speed of light. And it exhibits electric and magnetic properties. You might not be able to visualize those properties, but they are there. So electromagnetic energy, again, is anything that behaves mostly like light. It travels in waves, same speed, always the speed of light. And there's a lot of different energy levels that exist. So let me make sure that this page number is correct. So if you look on page 59, you'll see all the different types of electromagnetic energy. So it goes from very high energy with X-rays and gamma rays. Gamma rays higher energy than X-rays in this example. You've got ultraviolet just below that. You've got visible light. Then you've got infrared, basically heat, microwaves, and radio frequency waves. So you've got a lot of different types of electromagnetic radiation represented. Ionizing radiation is a specific level of radiation, especially in the electromagnetic spectrum, that's capable of removing an orbital electron. So we're going to talk more about the orbital electrons later whenever we're talking about the atomic structure, but basically the electrons orbit around a nucleus. So the electrons are these things on the outside. So if we have energy that is high enough, at a high enough level, then it can remove one of those electrons. And what that creates is an ion. So what an ion is a charged particle. So most of your atoms seek to be neutral, which means that they have as many positive charges as what they have negative charges. If you remove a negative charge, then the atom becomes positive by default. So by knocking one of those electrons out, now you've got a free-floating electron that is also a charged particle, and you've got this, and it's negatively charged, and then you've got this atom that is positively charged. So what you're going to have then is two ions, you've got an ion pair. So when we have ionizing radiation, that means that we've got an energy level that's high enough to knock out an electron and thereby make a pair, too, of ions that is an ion pair. So whenever we talk about being irradiated, that just means that you've intercepted ionizing radiation. And it's not something that you want to do carelessly. Since we are radiographers and radiology students, we're going to be exposed to ionizing radiation than more so than what the general public is. So what we want to do is we want to make sure that we protect ourselves in as much as we can from that ionizing radiation. So the cardinal rules to minimize your radiation exposure are to minimize the amount of time that you have to spend around ionizing radiation, or maximize the distance between you and the ionizing radiation. And if you have to be close to the ionizing radiation, to wear something to block it. So that's what we refer to as the cardinal rules of radiation safety for radiographers, and that is time, distance, and shielding. Minimize your time, maximize your distance, and then use shielding where appropriate. So again, ionizing radiation just means knocking out an electron and creating what we refer to as an ion pair. So I think this is the last thing I'm really going to have energy for. I'm running out of gas here. Is the sources of ionizing radiation. So essentially, you can break it down to two things. You've got natural, environmental, and then you've got man-made. So natural, environmental, you get ionizing radiation from a lot of different places. So you get it from cosmic rays. You get it from terrestrial radiation. You get it from internally deposited radionuclides. And we're going to talk about that in the next recording. So cosmic rays are things like from the sun. We're going to get ionizing radiation from the sun. You get X-rayed every single day that you get hit by the sun. But we also have terrestrial radiation, and that would be things like radon and building materials and concrete and things like that. So if you live in a place, you're getting some terrestrial radiation. But there are also other things such as deposits of uranium, things like that, plutonium. If you get into an area of the planet that is rich in that, then you're going to get more ionizing radiation than what you would somewhere else. And then you've got internally deposited radionuclides. You may have heard of things like carbon-14, which are that's the type of carbon that they use, or the molecule that they use to carbon date fossils and things like that. So those are internally deposited inside of your body. So your body is exposing itself to ionizing radiation. And you got man-made sources of ionizing radiation. And by far the largest contributor of man-made radiation is medical. So X-rays, CAT scans, nuclear medicine, things like that contribute the most to man-made radiation. But also we have industrial. With industrial we have if they need to look for cracks in airplane wings, then they use radionuclides in order to do that. Consumer products. The consumer products like your smoke alarms. Your smoke alarms have a tiny piece of radioactive material inside of that, and it's not giving you enough radiation dose to be concerned with, but there is a little bit there. And then from nuclear power, nuclear fallout, things like that. So if you look on page 6, you see a couple of pie charts that kind of explain where all that comes from. So we're going to pull it up there, and I'll record the next part of this and have it available for you before Wednesday of next week. I appreciate you kind of putting up with my breathlessness and my raspy voice. And again, I hope to get over this, and I hope to get back into class soon. I hope you're all doing well, and this isn't too much of an imposition for you. I assure you I'll make sure that you get all the information that you need to be successful for this semester. I appreciate your time. If you don't mind, give the video a thumbs up or any other video that you might view. If you are not one of my students, I appreciate a subscription and also a thumbs up as well. Y'all have a great day.